The setup for cornstarch. Okay, so last week Elizabeth, Charisse, myself, and Taysir were there for the second half, and a lot of people were very interested, right? And they came by and looked at the video.
And there were like 2 losers.
But nobody.
Oh my God!
No, not at all.
They were. No, exactly.
Because we're not going to get through this stuff. Hooke's Law is on your final either way. So if we don't get to it today, you're going to learn your own. So I think we should probably listen. The people all said pretty much, okay, we'll bring it back. They don't have it with them. Nobody had it with them that day. So that means that this Thursday is the day a lot of people said they would bring cornstarch back. I also emailed faculty. I got like 3 pounds downstairs. I got a few pounds up here, but Mr. Smith brought corn flour back, so I have to go return it. Cornstarch. So it's all right. It was nice enough to get it for us, and we can get like 5 or 6 pounds out of it because that stuff's more expensive. So what we're going to do is this Thursday set up again. Now, on Thursday, what Elizabeth mentioned as an example was to have a little Tupperware of the stuff, so people know what they're actually donating. So they have a mix of cornstarch and water, and they can actually see. Like you can actually just smack the surface, and it'll act as solids. It's very cool. So just to have it there as a demo. We had a video or a computer with 3 videos that were looping, so people could see videos of it. We had like little signs to hold up, but we also wanted to have like a big sign. So 2 things with glitter, sure. 2 things that we should have for this Thursday is a sign with some sort of, obviously attraction, and a Tupperware with the actual material. Now, I have enough material already that we can just use a Tupperware size full. So I can just send it with somebody. But I cannot, I'm telling you now, I cannot go on Thursday until about 5:30. I can only do the second half. I have to be after school for stuff on Thursday. Okay? So what that means, I know, and some of you have AP exams on Thursday, so you're going to be home for English. So 2 things. If you're in the AP English class and you're already going home and you want to just meet at the farmer's market, you can meet there to help, that's great. But I need people from school to actually transport the stuff over there. Like, for example, what we had last week was a laptop. We had the charger for the laptop, which you really don't need. I'll just charge it ahead of time. We had the little signs, and then we're going to need like the Tupperware with the stuff in it. And I'll leave it unmixed so you can mix when you get there. There'll be a table. Last time I got a table and I set it up and I borrowed it from somebody. I'll get that done during the day. But I cannot leave a laptop there. I can't just leave a laptop at the farmer's market, okay? So I need somebody to take it over there. So that means on Thursday after school, I'm going to need somebody to sign out the laptop for me and take it over there. If nobody can, that means that we can only do it from 5:30 on when I go over. And that's fine, but again, I mean, that's a good hour and a half where people could have donated or could have brought stuff. Anyway, with that said, does anybody, that's killing me. Does anybody, there's a bug flying around.
Yeah.
Does anybody know that they can be there on Thursday right after school, like leaving from school and going over?
I think I'm pretty sure not.
No, that's not your mom's birthday? No, your dad's either? Now, Edgar, if I send you over there with it, we just leave school at 3:30 and head over there. What's the earliest other people can be there on Thursday that can do this? If you can't, you can't.
5:30 because we have AP review after school.
Okay. You have AP
History review after school.
on Thursday. Okay, kind of like what we have for calculus study, same thing. Okay, I didn't know. All right. Can anyone else be there before 5:30?
Before?
Edgar, you need to go to APU's history review, Edgar. You can't miss that.
Wait, what day? What?
Thursday, there's AP history review, apparently.
Yeah.
So you need to go to that. You can't miss that.
Hold on, you said so Thursday.
We can just do 5:30.
No, I'll go.
She said no. You don't have AP English?
Well, yeah, but don't we get out early?
Yeah, but
You get out by like 12:30, 12:30, 1 o'clock.
like 11 then, like 11.
Yeah, we got out
Like it's short.
Because she didn't read the.
Trust me, guys. It's going to take you till 12, 12:30. Just trust me.
Before she didn't read any of the.
Last year it was not done formally and correctly. Just leave it at that, okay? Trust me. It'll take you till 12, 12:30 to do this. It really will. But you'll be out of school at 12, 12:30. I can send you with the laptop and stuff then, and then you can just go over to the farmer's market at 4 o'clock. That's fine. I don't mind that. So you don't have to come back to school to get the material. Yeah, I mean, can anyone else help her that's in English, that lives in the area, that doesn't mind?
If not, I'll just do it by myself.
I know, but you're just bored.
Think we're real with you.
I got it to do it.
Does anyone else live over there?
I sure lives close.
Are you in English? I don't know. Well, what you can do, Taysir, what you can do, what did you say? I missed it. What you can do is, you can go over there right from school and just meet Elizabeth over there, because you'll be home already, right? Because you're leaving at 1 o'clock, so you'll be home already. He's leaving school at 3:30 because he's not taking the test. So you're gonna walk over there anyway at 4 o'clock. You can just meet her over there at 4 o'clock, so she's not by herself the whole time. That'd be nice. We're not coming at 5:30 to help you guys. If anybody else wants to come at 5:30, anybody else can come. It's open to anybody else to show up there after your review if you want. Okay? Again, no, it's not mandatory. Just asking for some help. If we don't get the cornstarch we need, which it seems like we might be in that boat right now.
Stop it, don't change
I know I'm
it.
pessimistic, sorry, but it's the truth. We have about
You can
6
make
pounds of
Hey,
cornstarch.
Kenny, calm down.
We have 6 pounds of cornstarch out of 500.
It's okay, we can do it.
I hope we can, but I'm just not, I guess I'm not as hopeful as you are. But I hope we can get it. Okay?
Can we
If we don't, we'll do some other stuff with it. We're not gonna waste it. We'll use it.
It's eco-friendly.
Yeah, we were gonna do it like either the last week after school, one of those days, or after your finals, or even during your finals week, after you guys one of your final days, maybe one of those days or something.
You know that week, about that week,
What about it?
like, we have Monday, Tuesday, and Thursday our finals. No, Monday.
No, Monday, Tuesday, and Friday. So your finals, guys? Your finals? This is your last day here. Finals? Yeah, guys, come on, really. I know you're all contributing, but at the same time, that's not a contribution. Houston, go, now, outside. I'm not joking. That's not cool at all. I don't like that. Go in the hallway right now. I'll see you in a minute. That's messed up. You don't do that stuff. I don't like that, man. I really don't. Please. No, but you can stand out there for a minute. I'll be out in a minute to talk to you. Monday and Tuesday are final exams, okay?
No, that's the week after.
That's the following week. So Monday and Tuesday are finals. You guys work. This is your last day of work, I think, here.
Yeah.
Or is it this one?
Yeah, that one.
Yeah. Thursday though, you're doing a bunch of stuff on Thursday. There's like, I think, mass in the morning, then there's commencement practice after that. Senior sweep is after school on the 18th, from 3:30 to 4:30, okay? So you have work here, you have mass / rehearsal.
Yeah, so come to school fully.
You come to school for mass in the morning, like it's normal school, you come in dress code for mass. It's the last mass, it's a farewell mass. It's the mass last year that Julio and Jasmine spoke at. You remember last year the president, vice president, Shea spoke at? It's the same mass again. So it's going to be Jasmine and Karina Martinez. So we have exam, work, mass / rehearsal. You guys are done that day though, by like noon. It's a very early day.
Why didn't you know?
Okay?
wash my
Friday are your finals.
But why didn't they?
Kenny, I don't know. I'm just telling you.
Let it be. Huh?
I don't know, I cooked in lunchtime when I.
There's a napkin right there. You can just wipe it.
I don't understand.
Son, it's Tabasco.
They're making us take all of our
Just
files.
wipe it.
Son, it's Tabasco. Leave it at that.
Get my A's. And it's like, yeah, we're gonna make you still like the
Leave it at that.
I didn't talk to you yet, but I will today. I honestly haven't had time to, and it hasn't been the first
Just
thing.
leave it, Tabasco.
I'll ask him tonight, yes. Just remind me during
You
lunch if
haven't
I don't.
asked him?
Take your designs, Karen, can you go around and collect everybody's designs? Have your designs out, please. I'm gonna look at them, I'll edit them tonight, give them back to you so you can make any corrections.
Mr. Howell.
Karen, can you come around and collect your designs?
Hey, Byron. That's why I love you. What? She's not?
For this one, please pass up, guys. Please pass up your actual rough draft or whatever you want to call it. Oh, it's over there. Guys, if the stapler's not there, somebody's got it. Who's got the stapler?
Right here. Oh, well. Yeah, una caja y no sé.
Oh, it doesn't show
I'm gonna start writing the notes up, get them all collected, please. Karen's gonna come around.
Mr. How many use all your pencils?
Hey, I'm very thanks word.
Just gonna apply. Yeah, more coming?
Those are labs.
Well, you got the last.
You know what advice is?
Thank you, Karen, you're right. Why don't you take that next? You can take it after school from here. You said you had work. Yeah,
I'm about
you sure? Yeah, are the guys available? Did you ask them both? Ask them right now. Julian, Jason. Julian, Jason, you guys are able to meet after school today? Okay. Because I didn't realize how long I was going to take the call. You're going to run out of time. Oh, it's not yours. Sorry.
Yes, it is mine.
Well done with the attachments there. Anybody have their lab? I forgot to collect it on Friday, so it won't be late, but you need it today. Today's on time now. The one with the heat transfer. Okay, the one with the heat transfer.
I got you.
Again, it looks like this on the front. We did almost half it together. Check for her lab. Anyone else lab?
I got you.
I got you. The house. That's the problem.
Don't even think about it. Do not abuse that, or it will change.
I don't.
That's all right. I heard you said Liam.
Oh.
Oh, boy.
No.
Oh, man. Karen, are you 18? This is so
hard.
Wait. Karen, you're 18, right?
No.
Oh, man.
Any other labs that are not here, guys, are going to be considered one day late. Any labs that are not here right now, one day late.
Oh, no, I think I'm going to break.
Sorry? Ken, go grab a seat.
I am sitting here.
In your normal seat.
What the fuck is
In your normal seat.
Not philosophy, man. Become a philosophy major, just pretty funny, but I don't know how many.
Let's get started. Now, remember, a while ago, we talked about type of energy. We talked about different types of energy. I know you guys can discuss that later. It's a good discussion for later. We talked about types of energy. We said potential and kinetic energy. We also then later talked about the potential energy in a spring. Okay, and we used this formula 1/2 kx squared. What was k again here?
No, the displacement. The displacement.
How much has been?
One at a time. Good, the spring coefficient, or the spring constant.
I thought it was K. Oh, I heard X.
Okay? The other word, thank you. The other word for this, okay, you can say there's spring stiffness or the spring rigidity. Spring stiffness or rigidity are other words for it. Okay?
Didn't we use another word?
Coefficient, spring coefficient?
No, for
No.
Is physics college like it is?
Hmm?
So like,
You're taking all physics 1 right now, pretty much.
we gonna like, it's not gonna be crazy.
If you take physics as an engineer or something, you're going to take physics that has calculus involved in it. So you would take calculus first and then take physics. So you'll do this physics, but incorporating calculus. So it'll be
Physics
hard.
1 and then the ask question, whatever, just physics 1 is like this.
We're only starting vibrations, so we're going to be maybe missing the end of the year pretty much, which is not a problem really. It's a very easy topic. Huh?
Mechanical?
Mechanical, really. Yeah. Yeah. You know, what is electricity and magnetism? It's physics 2.
So
we're
No. Not mechanical engineering, mechanical physics, mechanics. There's physics 1, mechanics, physics 2, electricity and magnetism. This is called mechanics. Civil engineers use mechanical physics. physics also. So why is that the laws of government?
Rigidity.
Rigidity. Rigidity. All right, now, this is the interesting part.
Again?
You're starting over there? The interesting thing about spring, okay, that you don't notice right away, but we're going to actually do this. Listen, please. We're going to do this on Thursday or Friday here. We're going to look at spring stiffness to figure out how to determine it. Now, what you're going to notice, though, is I already put the formula on the board. F equals negative kx. So what this tells me is that the force is proportional to the actual displacement. And I'm using delta x there. Okay? The force applied is proportional to the displacement. So,
So the fish is proportional.
fish means proportional. Alpha always means proportional. Okay? The force is proportional to the displacement. The displacement. Okay? The force is proportional to the displacement. Question becomes, why is there a negative sign? Well, let me explain to you why. Do you know why?
Yeah.
Because it's acting against the displacement.
Very good. Absolutely right. Absolutely right. You know what he said? It acts against the displacement. If I had a spring, okay, and I took a spring and I held this part fixed, and I took this end and I pulled it this way, which way is the force going to want to pull back? Well, which way is the displacement? Thus, they're opposites, right? That's where the negative comes into play. Okay? Remember, this is the force of a spring. If you want to put a little spring down there. Okay, the force of a spring. Not the force being applied. The force you apply is some value, which is equal to the spring force, but we are concerned about the spring force, the restoring force. A restoring force means it wants to restore it to its original shape, or original size, or original dimensions. Okay? Let's look at an example here. If I pull, okay, if I pull down on something, let me explain this a little bit better here. If in a problem, I don't know why these are backwards. I pulled this image off the other one, but that doesn't make much sense to me. What they're doing is this, guys. If you take, this is the original spring here, they're saying. If you take that spring and compress it, it's going to want to push back out. That's what they're showing in this image. Again, if you take this spring and compress it to a smaller spring, and you squish it down, it's going to want to push back. If you stretch it out, it's going to want to pull back in. Okay, but the idea here is this. Okay, the idea is this. You have a spring. That's your diagram for a spring, by the way. It's a straight line, a bunch of squiggly lines, and then another straight line. That's the wall or the ceiling. So you have something hanging from the ceiling, and it's hanging on a spring. There's a spring in the middle there. Okay, now, that's going to get pulled up and down depending on what the mass is. So if we attach a mass at the bottom of this, with a mass m, okay, if we attach a mass, it's going to want to pull down on it. So after you attach this mass, what you're going to end up getting is something like this now.
It's gonna get longer.
Very good. Okay? Whoops. When you apply a mass, that's what happens to the spring. So this here, what do we call this when we looked at energy? What kind of length do we call this?
Why?
Wait, repeat that again?
What would you call this? This is something length. The what length of the spring?
Original?
Okay, original's fine, but the word we're looking for is really
Displaced?
Start with the L.
free length. Free meaning there's nothing acting on it. It's free to stand by itself. So this here, this we'll call this x1. x1 is the free length. Okay? Now, the spring gets pulled down on by this mass, right? And this is now called x2.
You subtract the
x2. And this is going to be our final length. So it's like initial and final. What should I do with those, Kenny? To get me what?
Get you the additional.
What's that?
Good, or the, well, let's say the delta, Kenny. The delta or the change, okay? Now, in the formula, F equals negative kx, that x is really delta x. Again, whenever you're doing these formulas, a lot of them in their books, in their textbooks, you're not going to see delta x sometimes. There should be a delta x there. So if you go back to the last page, That's why I put this delta x here, because this is really x2 minus x1. Okay? And some textbooks will write this. They'll write x minus x3, meaning the current length minus the free length. And that's exactly what we're doing, x2 minus x1. Okay?
What's the adjustment clause? I mean, isn't this the same thing we've been doing? We haven't been doing it.
Hooke's law is basically this.
No, but isn't it, like, yeah, I was saying, isn't it the same thing that we've been doing with springs?
Yeah, but before with springs, we had delta x, and that gave us the amount of energy that was stored in the spring. This is now saying to us, how much force do I have to apply to stretch the spring a certain distance? Think about it logically, guys. You see springs all the time. You know a pogo stick?
Yeah.
There's a spring in there. That's all it is. And the pogo stick. You jump up and down on it.
Okay.
Now, if there's a really small kid, like a 3-year-old, and he's really light, the spring is not going to go much, right? He's going to jump on it, and the spring is going to go very little. But if there's somebody like us, like an adult size, use a pogo stick, the spring goes like, all the way down. Because what are you applying? More what? More force. And remember, force is proportional to the displacement, or the squish in the spring.
What do you
Okay?
think displacement again?
Displacement, though, Star, is either one of these. Either gets pulled or it gets pushed together. If it gets pushed together, the displacement is negative.
It would be cool if you could go like that on the computer. You should like make something to do that.
Oh, isn't that the reverse?
No, but I mean, with the arrow used to have.
Look, it's a spring. It's a spring.
With everything in life can be modeled as a spring, right?
So, yes, that's the next one I'm talking about. Good, Ken. The interesting thing is that anything can be modeled as a spring, okay? And when I studied in grad school, my real field in grad school is vibration analysis. And everything you study has to do with springs. So for example, I know this sounds really weird, but just this bottle here, you can think of this as a bunch of springs that are all interacting with each other. Because if I hit the top, it sends a vibration through the rest of the bottle. Okay? So these are springs that are all connected, really. And this vibration causes another vibration, which causes another vibration. It's called a perturbation. Perturbation that causes other things to happen. So everything in the world can be modeled as springs. So for example, a very good application of this. Long time ago, I would say about 10 years ago, I was reading about this. I was in, was it 10 years ago? 7 years ago. No, 8 years ago.
We were like.
Sorry, freshman year of Villanova. I was taking a calculus class. I was taking Calc 4 when I was, yes, I was taking Calc 4. So I had a really good teacher, this guy Klaus Volper. I mean, one of my favorite teachers. I still remember everything he taught. Russian? He was Russian, yeah. And he had very, very light accent, though. Real good teacher. And what he did was he based all of Calculus 4 on engineering applications, which I loved because I was an engineer, so it was perfect. And he did everything with modeling with spring systems. And he told us a story, and I still remember it. And it was very interesting to think about. The model for a BMW, and I think it was like the late 90s, had a problem with it. When the door, or when the car would get up to velocity, I might have told some of you guys this in calculus. I don't think I've told in physics before. When the car would get up to like 70 or 80 miles an hour, the right passenger door would begin to vibrate. Told everybody in? Well, anyway, back to the story. It would start to vibrate, and it would vibrate uncontrollably. So, what they needed to do was exactly what you have in your car already. When you hit that speed bump, you have springs, your suspension or your shocks. The car's going to hit the speed bump, it's going to start to settle out over time, right? And then it starts to go flat. Because, two things. One, there is natural loss of energy to friction. Two, there's what's called a damper in the spring system. And a damper is the thing I always reference in the door. There's not one in this door, so I can't even use that. But if you ever close the door and you try to slam it, and as it goes to close, it's like,
Yeah.
and it goes slowly, that's a damper. There's a fluid in that cylinder at the top of the door, and there's a disc running over the fluid, which causes it to act like as if you're running your hand underwater. That's why the door slows down. So if you ever close the door that has a damper on it, as it's about to close, it'll go and shut. Because the cylinder, it's not on these doors, that's the problem. The cylinder is right here. It connects right here. So if you look at those doors, if you take a look at some of those doors, you'll see that the cylinder is the shape is cylindrical because there's a circular disc in there, and I'll show you a quick drawing. There's a cylindrical chamber.
Say ketchup real quick.
There's a cylindrical chamber, and focus, come on. Inside of the chamber, there's a rod. The rod runs through the center. The disc itself sits on the rod. Now, as the door closes, the fluid has to move past the rod. It's like taking your hand and sweeping it underwater in the pool. Do you feel that viscous force, the force that resists you from moving? Okay, ever try it? Go underwater, put your hand under like that. That's what's going on with the door. Anyway, back to the story. The door was vibrating uncontrollably at certain speeds, and DMW was very upset because they invested a ton of money into the research, and somehow this got neglected. There was what's called a natural frequency that they missed, and if you study engineering, you'll hear more about that. Similar to the Tacoma Narrows Bridge. Remember the Tacoma Narrows Bridge? It, like the disaster? That had to do with the natural frequency of it. So, they forgot or missed the natural frequency in the door. Now, in order to figure out the solution to the problem, all they did was actually attach a bunch of springs to the door. And they actually ran the door up to speeds like 80 miles an hour, and they were able to, with the computer, monitor the exact vibrations of every node. So they had springs on the inner, so here's the inner door, okay, with a handle on the door, on the inside. They had springs everywhere, a bunch of springs, and we're talking like hundreds of springs. Based on the, listen guys, based on the motion and the vibration of those springs, they were able to tell what the natural frequency was of the door that they were missing. And then they went in there and they actually fixed it by changing the inner workings of the door, the mechanisms that are actually part of the door. They changed the material properties. They might have, instead of using a certain metal, use a different metal. They made it less mass. They did what they had to do to fix and solve the problem. This is like the best engineering application you'll ever see, okay, because they modeled it with things like springs. They took something very small like a spring and they were able to use that to globalize or to look at the whole door itself. They looked at all the data from every spring and we were able to connect them to each other. I don't know. I forget, actually. I completely forget, yeah. I think it had to do with the fact that, like, it was in the 90s, there was an airbag on the one door, but not on the other door. That was one of the big differences that they didn't account for.
Well, you know how, like,
Forget what it was.
You know how, like, some cars back in the 90s, they only had mirror driver's side, and then the passenger side didn't have a mirror?
I've never seen that.
You never seen that?
Is that just somebody's car that got broken off? They
No,
fix it?
no, you know what actually I'll do?
Never seen it. They used the rear view for the right.
Look it up, Honda Civic 1991.
Oh, back then. Oh, yeah. Okay. I think that now there's cars like that still. I was like, I don't think I've seen that. But that makes sense, because that was a while ago. But anyway, there's a lot of things that affect it. Now, next thing. One of the most widely used devices in physics is called a spring scale. Okay? A spring scale. And they have it at the group. You got that was my application right away. Go to the grocery, okay, no, I'm glad you know. I'm sorry. You go to the grocery store. You want to buy what kind of fruit? Tomatoes? Tomatoes, both tomatoes.
I was gonna say pomegranate.
Pomegranate, okay. So, normally it's priced per pound. Some fruits, though, is per individual item. Like some oranges, it's like $1 an orange. But if you get like bananas, they're like 59 cents a pound, right? So, you get your group of bananas, you walk over to the scale, you put it on the scale, you see the scale go like this, right? And you see that scale fluctuate, and then it settles on one spot. There's a spring in there that is stretching based on the scale. This is a perfect example of it. And now, here's how it works.
Like with shrimp.
Along, yes, like the shrimp guy also, yeah, same thing. So here, along this scale, listen, that's your zero marking. And what will happen is this. If there is no force being applied whatsoever, it will be back at the zero marking. Clearly here, there must be a force because it's not at the zero. So let's assume there's an item at the end of it. Now, if that item gets bigger, what happens to that red marking? The red marking moves down, right? This only works because springs are proportional. Remember, F is proportional fish. proportional to the delta. That's the reason this works, because it's proportional. Without proportionality, this would not be true. So, based on what I just said, if I applied a mass of m and it moved from increment 2, 6, to increment 6, how far is that? 4 increments, right? Now, sorry, not 6. 1, 2, 3, 4, 5, 6, so it's 8. I counted 6 up. So it goes from 2 to 8. So my delta is what? Is 6. What if I apply, or I put 4 bananas? What if somehow I have the exact same 4 bananas? The exact same 4. Put them on. How far is it going to go now?
6 more.
6 more. Why, Kenny?
Because they're exactly proportional.
That's the definition of proportionality. Again, if I apply a force and it stretches the spring 7 centimeters. If I apply double that force, it'll go 14 centimeters. If I apply triple the force, it'll go 21 centimeters.
What about 1/2 the force?
It will go, instead of 7 centimeters, it will go 3.5 centimeters. Half. So what you want to think about is this.
3.5.
This is like your y value. This is like your x value. If you apply a force of 500, newtons, and this is meters. If you apply a force of 500 newtons, and the spring is able to stretch 10 meters, that does not look like a 10,
What?
10 meters, if you know those 2 data points alone, you know everything. You know everything. Again, by the way, put a delta here, sorry. I know I'm just putting x, but let's put a delta. Okay, so we know we're talking about delta x. So, yes, as Star just said, 1,000 would be 20. 750 would be 15. Good, Star. Because halfway between 500 and 1,000 is 750, so it'd be halfway between 10 and 20. Proportionality is the key for Hooke's law. That's what it's all about. Why is it proportional?
Think about it.
No, it's a good question. It was experimentally solved. Let me see if I wrote down why on here. I wrote down my notes, but I don't think I actually went over why. Yeah, you know what it was? It was just experimentally determined that it was proportionality. Just like, remember, F equals mu Fn, force of friction equals mu times normal force? That's also experimental data, that's proportional. That's all that is. Experimentally has been determined. If I look it up and I get another answer, I'll let you know. I don't know if that man knows, I can't answer that. Let's look at an animation. So, let's discuss how we filled this out. If you know the force is 500, and you knew this was 10, when you double the force, you double the displacement because of proportionality. If you find a force halfway between here, what's the displacement halfway between here? 15. If I did half of 500 and made it 250, this would become not 10, but 5. Okay? Now, given this data, find K. Given this data, find K, the spring stiffness. Use your formula from the last page. Go back to your formula for F equals, and find K. And you'll pick up on it right away. I know, some of you know it right away.
You gave us like 3 formulas.
Go back to the original one. F equals Kx. Negative Kx. Sorry, F equals negative Kx. You know F.
Are we trying to find the positive?
You know the X value or the delta X value. Find the K value.
Should we make it positive? Make it positive?
Don't worry about it for now, the sign, because again, these forces would all be negatives. These forces would all be negatives because they're pulling it, it's moving down, so it's pulling in the opposite direction, or it's moving right, so it's pulling in the opposite direction. They're always going to be opposite.
Oh, it's this?
No, he said K.
Figure it out. You
What?
can figure it out. Look at the units.
Wait, force?
And over L.
No.
No, force over meter. Newton's over meter.
Right? Are you doing F divided by delta X?
Newton's over meter.
Good. Newtons over meters. You were thinking of mass because you saw the M there.
You changed the sign.
Because you don't put. You said original. Delta X.
Either way though. Delta X for X. Those units.
So then, Mr. Hodge, you just changed the sign. Yeah, he did. He said it's gonna be negative because it's pulling down. So then.
Again, guys.
It's not negative K. That doesn't make sense. That has to be a
No,
negative.
not at all. Watch, ready? Let's take a look. We have F equals negative K
Wait, why
delta
is it
X.
negative
The question was, let me explain again. That's what I'm going over right now. The question was this. If I don't do this, if I leave them all as positives, I'm going to get a negative K value, which you can't have, obviously. The reason is this. If an object is being pulled downward or pulled upward, the restoring force is opposite in direction. So this is telling me here, see how these are positive lengths? This means that I'm looking at a spring that has something to do like this. And I pulled it as far as this goes, and it made my delta x 10. So I went from a spring that was a free length of this to a free length of this. And that's my delta x equals 10. That's the first case. So I'm drawing an image for the first case there. Now, if I pull this spring to the right, which way does it want to go? That's why the force is negative. Because the force has to do with the spring force. Which way is the spring pulling back? Negative. Negative to the left. Which way is the displacement? Positive to the right. Okay? That's why this is going to be negative. So you're going to have negative 500 newtons equals negative K times 10 meters. What happens to your negatives? They cancel. Okay? Now, divide through, make the negatives positive. You get 500 newtons over 10 meters equals K. So what are your units? Your answer is 50. What are your newtons? Thank you. Newtons over meters. So what are your newtons? What are your units?
So because there's negatives on both sides, it's positive.
Exactly. And that's the whole idea. The spring constant is always going to be positive, no matter what. No matter what. Because again, so you need to remember that this F here is the force that is being responded by the spring. So even though you're pulling it to the right, the spring is pulling it back to the left. That's why this was a negative 500. Remember, to the left is negative for forces. To the right is positive. Okay, F
You
equals
just
M.
assume by looking at the problem, it's both negative on both sides.
Yes, but Star, if I pulled it to the left, now my displacement is negative, but the spring is pulling back this way. So the spring would be positive. So this would have been a positive, this would have been negative, negative, which is still going to give you positive. No matter what, K is positive. Again, K is your spring stiffness. It's a material property. It must be positive, like the coefficient of friction. Similar to the coefficient. That's good. You get better? Can that wait? Okay. All right. Does that make sense? I want to look at an animation of this now.
Mr. Howe, but that was, it wasn't going towards down. The force is going down, but it doesn't matter.
The image we showed was vertical, but yeah, it doesn't matter. If the weight is pulling it down, the spring is pulling back up. So the spring is positive in the next. If you're looking in the vertical, then it's delta x in the vertical, and it's f in the vertical. Same thing. All right, so let's take a look at this image now. And all it's showing us is an oscillating spring. It's just sitting there oscillating back and forth.
What's that arrow?
Okay? The arrow is showing the indication of the force. Because, watch what I do here. If I hit stop now, the spring is being pulled this way, right? By some body or some external force. So the spring wants to pull back that way.
So isn't the
Back that way. Guys, why don't you separate each other so you can focus a little more? Maybe somebody should come up here, just so that we're all, shoot for it. Odds are even 10 bucks. So, here, if the object is being pulled to the right, it wants to go back, because the spring is a restoring force. So this arrow you're seeing here, this arrow, that's the force of the spring, Fs, at any given time. So when the object, when the object is pulled this way, the spring pulls back this way. When the object goes past the free length, here's your free length, right here, 0. When the object goes past the free length, now it's compressing the spring, right? So the spring wants to do what? Push out that way. So when we do that, we're going to see the spring push back that way. So now the spring is being compressed and the force is pushing to the right. Because again, the spring is now compressed. Here's the free length. Here's the center of the spring of the object. This center is past the free length. So it's by default being compressed. What happens when they line up? When they line up, there's no force. Okay, there's no force.
I thought we learned this already.
We did.
You definitely saw this in physical science. Absolutely, you should have.
This way.
Yeah, earlier in the year.
I don't think we did Hooke's law though. I think we just did the energy.
But I remember when
I
we
know,
did
but you did that.
the.
Did I bring springs in and stuff?
Yeah, you showed us.
Yeah, I think
You
you
just
did.
used the pen, no, you
Yeah.
have,
It was free. We didn't talk about the formula.
You did, you
Okay.
ran out your pen.
Okay. So what we did, yeah, was the energy. We didn't do the Hooke's law. That's the difference, yeah. I remember doing the energy stuff. I totally remember doing energy. But we didn't do Hooke's law. Yeah, potential energy. On the spring. It's right there also. Yeah, but nothing about Hooke's law, right? Okay, that's fine. It's good that we're remembering this, and it's not a bad topic to revisit because it is used a lot.
Mr. Howard, you say that the force,
It's from the
you
spring.
changed it, okay, anyways, the other direction, and the arrow's going that way. And you said that the force, the arrows, whatever way the arrow's going, you said the force is going this way, but the force being applied is going that way.
Yes,
So
and the spring is equal and opposite reaction, Newton's law.
Is it X?
If it's moved over here, star, X is positive because it's moved to the right, and then the force would be negative. So you'd have negative, positive, the negatives would cancel out.
But why isn't that the force, it's like, the force, is it coming from where the force is like coming from?
No, exactly. It's coming from the spring's restoration. Because we're looking at the force of a spring. We show that the force exerted on a mass by a spring. So take a slinky later, pull it apart, or some sort of spring, and you'll notice it wants to pull back together. So the spring is being a contractive force, whereas you are an expanding force. Okay?
She was showing me that's her spring.
So this is a good example of a spring, guys. When I pull this apart, I'm not going to pull that much. It wants to pull back together. So the force is pulling back together, and let go, it comes back together. I pull it apart, it comes back together. Pull it apart, it comes back together. Now, I can't really compress this one that much, but it kind of pushes back out. See how it kind of pushes back out? Like, yes. But rubber bands only work in elasticity. They don't work in compression. Okay, spring. I'm going to bring this stuff in on Thursday and Friday, so you'll be able to see it.
So that's compressed right there, that's compressed,
Exactly.
so the force is going there.
Mm-hmm. Exactly.
When are we in access?
The guys are taking their exam for school today. I should have them graded by for you. Right tonight, I'll put the grades online, and Thursday, come back.
I'm a little late because I put on my thing as soon as
For work study. Okay, maybe you can do that during lunch. Is that possible? Can you ask Ms. Montanello?
They told me come during, at school.
It's fine, and if you can't, you do that. But maybe during lunch, you can ask Ms. Fernandez or Ms. Montanello, go up there and say, I'm supposed to make up a test with the group, so they are waiting for me. Is it okay if I do it now?
Yeah, but I just want to tell my God, man, I gotta go to work. Serious.
You want edgy?
Either way, guys, those who are doing the makeup, look here at the class. Let's continue with this stuff for now. Now,
I gotta be at 5.
the other one I wanted to show you,
5.
forget what this one is. Let me just check real quick. There are a few others I wanted to see.
A little prayer service. Oh, no, I don't want to do prayer service.
Okay. All right. The reason I pulled this up last year, I remember this link that I used. The Hooke, the law you see for Hooke's law is very, very simple compared to what's really going on. Here's what's really going on. If I solve this formula for P, I get P equals that little delta symbol, it's a lowercase delta, over L with an A and an E up top. That's what I would get for P. Now, the delta symbol is really your X value. This is really your force. Do you see this part over here? AE over L? That's what K really is. I want to make sure we're clear now. This is like your force equals, this is like your delta X, and this is like your K value here. Okay, there's no negative sign there. Don't worry about it for now, please. The delta X value is really this delta symbol they use in mechanics. Come on. Yeah, obviously, because people are talking. P is the force. Okay, P is the force here. AE over L. A is the cross-sectional area. L is the length of the spring. E is what's called the modulus of elasticity. It's a material property. You can just determine it by the material. So the K value, even though I call K a material property, K really has to do with the cross-sectional area, the length of the spring, and then its material properties. Okay, this is really called Young's modulus. You don't need to know these terms. But I want you to know that K is really a bunch of other stuff lumped into one parameter. Lumped meaning they're all put together. Okay, so K is not just the spring stiffness. It's really the spring, the length of the spring, the cross-section of each coil, but we're not going to get into too much detail. So you're just going to be using K as a whole. But know that K is a lot more than just some value. There's a lot more to it.
So physics and college, they go into detail.
Yes, exactly. So when you study in college, you're going to look at all these values here. Okay, you're going to look at all those values. Let's see, what are the other ones that I had? I don't need tensor form. Okay. No.
A lot of stuff about that. I can do this. I can't do
The
this.
test will be the last section on the final.
I'll put a few of these on the final, that's all. But it's not going to be counted as a test, because we're just going to pretty much do this, that's it. The next few days are all just reviewing other stuff. All right. This is a really good diagram. This is a good engineering application. You've all seen this before. You've all seen it whether you know it or not. Now, the idea, you can read through it, but I'm going to explain what it says. An object will stretch until it reaches what? Its limit. Its limit. Its limit. Now, this here is showing that there's a limitation to it. So the object will continue to stretch until it hits a limit. And then what's going to happen at that limit?
Isn't it gonna lose its form?
It loses its form. It becomes permanently deformed. Permanently deformed.
Oh, you just sit down, it won't.
Yes, it starts to slinky, it won't come back to its shape. It won't come back to that compressed shape. A slinky. If you want to ruin a slinky, take a slinky and try and like pull it across the room. It's eventually going to start to deform. It's going to go beyond its elasticity limit. Think about a rubber band now. Think about a rubber band. A rubber band, it will not permanently deform. It might start to get over time less elastic, but a rubber band, it doesn't really deform. It breaks. It reaches its yield point, and it will actually snap. Okay. So what you'll see is this. Take a rubber band and look at it on a close up. Stretch it. You'll notice the cross-sectional area gets thinner, right? It gets thinner and thinner if you stretch rubber band. Eventually, it gets so thin that there's not enough strength. Tensile, because you're pulling in tension, not compression. There's not enough tensile strength, and it will then snap. That's what this diagram is showing. Okay, this is a very important diagram in engineering. It's used all the time. Okay, all the time. This is where Young's modulus comes into play, by the way. Let's see if they even mention it.
symbol on the top left?
No, they don't mention it.
What's the top left symbol?
Wikipedia?
Tau. Stress and strain. This is the stress applied, this is the strain. More about that if you like to on your own. Not right now, though. Hysteresis. Okay. So, the idea of hysteresis is this.
You need to stay on that.
The idea of hysteresis is this. Even if an object doesn't permanently deform, by using a spring, it becomes less elastic. And think about it logically. Girls, your hair bands. Eventually, over time, do you have to get rid of them?
Yeah.
Okay? And you're not stretching them too far, but eventually, they kind of stay in that form, right? It's the same, Chloe.
They're rubber bands. They're not just springs.
You said it's a weed, you hear me?
They're not. You said
It's like getting rid of weed.
It's not a spring in pressure, because you can't push rubber bands here, but it's a spring in tension, you can pull it apart. So, on your car, I've had my car burst me for 4 years. Yeah, 4 years now. It was my older brother's car before I got it from him. He had it for 4 years before that. Now, the shocks on the car are not the same as what they were when you got the car. And you notice that, obviously. So, you might say to yourself, the spring is not being deformed, but it's losing some sort of elasticity. Its K value is changing as a function of time. As the limit of T goes to infinity, as time goes to infinity, the actual K value will alternate. It will change. It might become less and less over time. So you'll notice that your car might now not respond to speed bumps as well as it used to because of hysteresis. Okay? That's the reason why. Like the school bus. Yes.
It also depends on the conditions of the tires.
Well, yeah,
Sure. There's a lot of other stuff.
My dad, like, you know how a highway is
Have a good day, guys. Homework. Make sure you get your sketch if you haven't so far. And then tonight. Then, so do Thursday, late, one day, Thursday, late.
remember that.
Your dad went to New York?
And like, I remember like the highway.
Uh-huh.